Goedemorgen allemaal. Welcome to HDE 300S. We are continuing and we finally mornings. Are you? Morning, Mr. Dol. Didn't see you join now. Yeah, it's our second last chapter. Yeah, I mean this. Yeah, and then we have chapter the gating next, which is I don't know who sets up these things. Really, but gating is going to be next, which is chapter 12, I think, from what I remember. However, for your test, which I'll obviously discuss at the end of the lecture, we're only going to be doing 2 chapters, which is this one, your crank F diagrams and your forces and torques, right? Well, there's enough questions to assess you on. And then chapter 12, which will be the gating chapter, which will be covered in when is this? Next week. And that'll be obviously for the final. Okay. Realistically, this chapter is I was having a lot of issues trying to explain it. But I'm hoping that you guys can fill in the blanks for me with certain things. Not really fill in the blanks for me, but I mean, like, I hope you guys are gonna get it, because it's not like the previous chapter. It can be a bit weird. So one needs to really just kind of follow and kind of pick up, just go with the flow really, and see. One can't really gauge if they're going wrong. Okay, they can actually with the maths, but I mean, it's one of those chapters. It's not too bad though. Okay, so let's begin. So, like I said, chapter 16 in your textbook. Let's see if you want to follow. So, guys, obviously, who can identify what that is there?
Is it a flywheel, sir?
Yeah, obviously, yes. Have you guys any experience with flywheels? You guys know what a flywheel is used for?
It's supposed to store energy, sir. Rotational energy.
Is that all? Is that what you know it as?
That's what I know it as, yes.
Okay, great. That's a good start. So luckily, we will unpack it even further. Mr. Bali, Mr. Batoso, you guys, do you have any experiences? Do you know what a flywheel is? Okay, guess not. Silas, Shipingana, Nangolo.
Yeah, yes. Yeah, it's exactly what Kifa said there. It's to store energy. Yeah.
Just store energy. Store energy. Why? For what? For who? Is it a battery?
Yeah, to keep the momentum of the. How should I say? Yeah, to keep the momentum of the rotate.
No, not to convert Lenny to motion. No, not that. Yeah, but okay. So, fortunately for you, I'll try my best to kind of explain what a flywheel is exactly used for. Yeah, and yeah, let's see what I can do. Okay, so do you guys remember this formula? You know the FP times R sine theta plus sine 2 theta with 2n. You should know this formula very well. For sure, it's gonna come in your test in exam. That is your effective turning moment. Remember that torque formula? The purpose of the previous chapter was just to use this formula. Do you guys remember this formula by heart already? So where we're heading off is that if we were to plot, for instance, from 0 degrees to, let's say, 2 pi radians or 360 degrees, or let's say for a full cycle of operation. That's what we're gonna. So we have obviously our FP that stays the same. Obviously, it changes depending on where you are. But the idea we plot. So we plot torque with respect to theta, or that angle there, right? Or the crank angle, obviously. If you do that, and obviously I'm saying I'm assuming a single cylinder double acting steam engine. Don't worry too much about that. Obviously you're gonna get some kind of curve. Right. So you can see the curve with this. So that's crank angle and the turning moment. The right turning moment meaning it's that torque which you found. What this is called your crank effort diagram or your turning moment diagram. Right? So the whole point of this chapter is to really just look at these diagrams and do analysis on them. Right? So I guess it's an advanced topic because the photo source and sister not happening. Sorry. Like I mean, in terms of real life applications, not so easy to really kind of just use. One must really know what they're doing. So anyway, so what a crank effort diagram really is a graphical representation of the turning moment, the crank effort for various positions of the crank, right? And it's plotted on coordinates in which the turning moment is taken as an ordinate and the crank angle. I'm not sure, but the idea is that we have x-axis crank angle and y-axis the moment. So what I want to make you aware of, you see that mean resisting torque? You guys see that line, that straight line? Good morning, Annalisa. Annalisa Kamveletu Tswania. Morning. I like when I see you guys log in with your official Blackboard stuff. I can actually see your full name. Louis Alberts Vormerans. Just some parents who are playing with us. So you guys see that that straight line, right? That mean torque. Remember we've talked about mean torques and strengths too. I hope you guys can see it. It's a straight line from A to F. And I want you to view the torque as such, right? So I want you to keep in mind, and I'll try to repeat it over and over. So that crank effort diagram, which goes from a small a to a small b, small c to small d, and small e. I hope you guys can see that. The whole curve. Treat that as your drive torque, right? And your T mean, treat that as your load torque. So obviously I had a small image there for you for you to understand. So our input is this curve, this cosine sine curve. However, there's a straight line. You know that A to F. Mr. Doe, do you see that A to F? Treat that as our output. Are you guys following me? Please let me know you're not following me, because that's like a very important part of this whole thing. Is no one seeing that? Mr. Kiefer? Mr. Matoso? Yes,
Yes,
thank you.
I can see the A to F.
Okay, great. So what I mean is basically our inner torque is fluctuating, right? Our turning moment. Yeah, and then big A to big F is a low torque. My question to you is, if you look at the diagram, right, you see you're having a positive and a negative moment, right? Right? And I mean, just thinking about it, good morning, Bradley Russell Haddad. And just by looking at it, I would say we have from B. I haven't started the lecture, so I'm kind of prepping your mind for what it is all about. From big B, small b, C, right? The first bump on the curve, that's an excess of energy, isn't it? We have more torque than required. You guys agree with me? And likewise with these big D, small d, big E, capital E. You guys see that the two things above the mean basically. Oh, can you guys see that just looking at the diagram before we actually begin? Thank you. So at big C, small c, D, we have less torque than the mean. Is that correct? You agree with me, guys? You agree with me, Louis? Anati, you guys see it's below T mean. Obviously, that means we have less torque than required. We have less than a low torque. Is anyone saying anything? Okay, so what I'm trying to tell you is that before we actually begin, what that flywheel is doing, right? That flywheel is making sure it stores energy when we have excess torque, and when we have a deficit amount of torque. That's when we engage the flywheel to supply that lack. Can I just say that again? So the central premise of this whole chapter is that your input torque, your drive torque is fluctuating constantly, and obviously we require to have a constant torque, right, on our output side. But on our input side, because our torque is fluctuating, there are times when we have extra torque and excess in torque, and we have a deficit in torque. So what we do is, in times of excess, we store energy in the flywheel, and in times of deficit, we release energy in the flywheel. Does it make sense? Are we following, students? Yes, we're going to get to that. We can also get to that, yeah. Because I mean, obviously, these two it's kind of like a I wouldn't say like a clutch, but like something in between to kind of maintain certain things. Okay, so that is just slide 3 of 58, and let's move on. So that is just me talking to what holistically we're trying to achieve. Because a lot of the calculations are essentially based on this diagram and the flywheel. So I didn't want to talk. What I'm basically saying, just give me a moment. Oh, my throat is moving me. I'm getting worried now. Okay. So before I actually started, I just wanted to make you guys aware, like, exactly what is happening in terms of the diagram. But obviously, all of this will explain now in detail. So I did mention here the mean resisting torque equals the load torque, right? So that's what I want to make you aware that treated as a load torque in that diagram over there. So drive torque is fluctuating, and the load torque, it's a constant, typically a constant torque. And there are times when there are less energy and times there are more energy. So they're saying the slider crank mechanism, obviously, this is just relating, this is following Courbet's train of thought. And obviously we're using slider crank mechanism, and it uses a prime mover for compressors, punching machines, obviously for engines and things like that. Yeah, basically, that's a very common kind of mechanism used for many applications. But essentially, what gives birth, what the slider crank gives birth to, is this diagram, which is a crank angle turning moment, right? Which is roughly discussed. Okay, so first point on this, we obviously pick up. It's basically all that I'm explaining now is basically what I explained to you in that one slide. Is basically I'm just unpacking each part now. According to the textbook is giving. So I don't want you to ever get confused. Don't want to start talk, and then come to the point. Just give you the point and just elaborate. So here we see the turning moment is 0, when the crank angle is 0, and it becomes a maximum at 90, and it becomes 0 again at 180, which is it is a maximum when the crank angle is at 90. Oh, then it's 0 again at 180. Yeah. What they're basically saying here is that from small a, b, c, that represents, so remember we're doing a double acting thing. So the outstroke, that will be the outstroke, right? And then the instroke, that means going from bottom to top, is C, D, E. So what we're just seeing there is a double acting single cylinder, and we can see 2 strokes, right? So obviously you go unpack. You can obviously imagine what that is, right? It goes to the top, comes to the bottom to the top, and so forth. I threw this in here because maybe not at the right place, yeah. But just as a backup, remember that work done is also represents as rotational work done is also torque times angle, which is analogous to force. Let me just quickly see. Work done is force times distance. So for work done in rotational, it's torque times omega, right? That's nearly same as force times distance. Yeah, so it's the same kind of thing. Obviously, it comes out as joule, which is Newton meter, which is also obviously power as well. Power is also in that same, but power is with speed, which is force times velocity. So this is torque times an angle, which will give you work, and obviously you take that times the speed you get. So, what it's saying is, since the work done is the product of the turning moment and the angle turn, that's why I threw that there in. So remember, at the end of the day, we're going to be looking at joules here. Joules will be the unit of the day, right? So the area under the curve, what it actually represents is the turning moment diagram represents the work done per revolution. So I think that's not actually it's being hidden there. Excuse me. This diagram was just to show you more than anything else, which obviously see in the diagram. And they say in actual practice, the engine is assumed to work against a mean resisting torque shown by the horizontal line AF, right? Obviously, we discussed it. What we mean is that is the torque required by the load. So it's working against it, right? That's the way they're perceiving it. And obviously, we also looked, so they're saying the height of ordinate AA, small a to big A, represents the mean height of the turning moment diagram, right? Obviously, that's the mean torque basically, which is the same as EF. And they're saying since it is assumed that the work done by the turning moment per revolution is equal to the work done against the resistive torque. So therefore, the area of the rectangle A, small a, big A, F, and E is basically the work done against the mean. So it's basically the whole bottom part is the work done against the mean. So work essentially required for the load to drive, right? So that whole box of small a, big F, small e is essentially just you know, the work done, the work required, right? Or the work done. So from the diagram, what's important to know that is why I had a small image here. I was gonna just make sure I place it. It's obviously why I want to refer to the diagram as a talk. Still I'll just remove this. Is that, let me just take this here and look like this. When the turning moment is positive, right? So that's from small b. Obviously, we talked about above the mean line. That's what they're saying. When the engine torque is above the mean resisting torque, obviously that's between points B and C and D and E. What happens here is that they're saying the crankshaft accelerates and the work is done by the steam, right? It's also touching into the flywheel, right? So what it basically means there, just throwing it in before we actually get to it, is that that's the time when the flywheel absorbs its energy. So the flywheel will absorb kinetic energy at those particular points. At number two, what they're saying is that when it's negative, and we obviously agree with the saying when the engine torque is less than the mean resisting torque or the load torque, that is happening between C and D. And at that particular point, we find our crankshaft actually releasing energy, and that is basically it decelerates and it gives energy. So they're saying the crankshaft retards and the work is done on the actual steam, right? So obviously we're talking about a steam engine. I don't know why they use it in particular. So what's particularly important from that also is that T mean, they're saying that when T mean minus T mean, which is the torque at any instant, minus T mean is positive, it accelerates the flywheel, and when it's negative, it retards. So basically, that just means on top of the curve and at the bottom of the curve, right? That's what we're actually just kind of heading to, which I just mentioned essentially prior. So that's particularly, you'll see why is it all important as we talk, as we go along. But does it make sense as to why the flywheel accelerates and why does it decelerate between those particular parts? Mr. Matoso? Simple. Because between from B to C, we need to absorb the energy, the excess, and then obviously we have to now again release the energy at C to D. Is it all clear to everyone? Mr. Doyle, Silas? And what they're basically saying, looking at the graph, what it's just basically saying is that T minus T mean, so any point on the graph is just the top of the side is accelerating and decelerating. That's what it really means in a nutshell. I don't know, it's whatever they're trying to say here. So I'm just kind of obviously following the textbook. Okay, so not only for double acting steam engine, thank you. We obviously have turning moment diagrams for 4-stroke engine as well. And it looks like this. I'm just showing you different types. We have the intake or the suction, the compression, and obviously the working stroke, which happens. It's also the combustion stroke, right? So that's when it's expanding. So just looking at that as well, having a similar thought that they're saying for 4-stroke cycle internal combustion engine, there's one working stroke after the crank has turned to 2 revolutions, right? Or 4 pi radians, not 4 radians, it should be 4 pi radians, right? Maybe that's just like a miss thing on the slide. Right. And again, here you can see from this is that only this section here where the working stroke is, that's where most of the work is generated during expansion, right? The working stroke, which obviously when it's a power stroke, when it's being pushed down, and then we have a lot of you have a negative at compression, even at suction. Okay, we have a bit of work done there, but normally typically the suction and exhaust they normally characterize as negative work, but all the stuff will be unpacked. But I'm just giving the philosophy of what's happening. Obviously, T mean, that'll probably be maybe the drive shaft or whatever, or the loading shaft, and obviously anything above the line, and obviously anything below the line. So we'll be looking at this individual analysis, and what we're really looking at, we're actually looking at what's the mass of the flywheel, what must be the thickness of the flywheel, etc., etc. So we will look at that. That's where it all basically comes from, and it's obviously your mass moment of inertia. So I'm just making this another diagram. Another diagram, obviously, that's a more realistic one. I just found a realistic one, figure 1A. It doesn't look so smooth. It has just small bumps. But basically, what's really important is to note that expansion stroke, that's the only place where the work is done. And again, on the other one, like they're just using triangles, a little bit things easy. Obviously, going through 4 pi radians. Obviously, we'll be looking at a 4-stroke ICE towards the end. And again, anything above the mean line is considered excess energy, right? And that energy we absorb, obviously, that's the energy which gets released during the different times in the so-called suction, compression, and exhaust stroke, right? So I don't know if Mr. Kiefer meant, I don't think he meant, but I'll help him stop him spinning out of control. But I think that really comes to the part of keeping it in control, that it has to operate at a specific torque level, right? And the flywheel kind of does that. So again, that is just the philosophies here. And then just talking to this again, the exact thing. Basically, since the pressure inside the cylinder is less than atmospheric, during the suction stroke, a negative loop is formed. That's on the suction side, right? That's negative. Coming back, the same to the compression stroke. The work is done on the gas. Even if you remember our notation, when we did thermal stew, when something was compressed, it was typically negative. And also we have another negative loop there. So there's no work being done. In fact, it's below the mean. But then finally, during the expansion or working stroke or the power stroke, the fuel burns and gases expand. And obviously that's a plus, and a large positive loop is formed. In the stroke, work is done by the gas. So remember all of that in thermal stew, work is done by the gas, on the gas. So that's where the work is done. And then during the exhaust stroke, the work is done on the gases, therefore negative loop is formed, right? So again, so the only positive part is here. Then they say it may be noted that the effect of, okay, it's also taken into account, obviously in this kind of in this place, which is the FP times torque, whatever. Again, more diagrams. This is for vertical steam engine, and I'm just accentuating over and over when there's a surplus in energy or excess, and when there's a deficit, right? So again, above the mean, above the load. You can see I'm just quickly showing you times when there's more energy, there are times when there's less energy, right? Again, same with the ICE, same kind of story, right? And then again, which we'll be looking at multi-cylinders particularly, and we're also looking at the 4-stroke. And multi-cylinders, you have this nice curve. It's fairly easy to use. You have the mean line, and you can see A1, A3, again, is where we have a surplus in energy, and again, the deficit in energy. So this is what we're really going to be looking at, right? Okay, so we're getting to where we need to be. Okay, this is just really a slide through an extra, but is it worth talking about? I'll probably have to just talk to it. But it just uses our turning diagram, and I'll just quickly just elaborate on this. Nothing really. It's more like the application of it, which I was trying to really just highlight, but I'll just make the font bigger as well. Wasn't really. I think the concept is brought out there, but I've said it a few times. So the area under the turning moment diagram represents the work done per cycle, so that's really important. And the area by the number of cycles per second gives us the power developed by the engine. So it's the work done per cycle, and obviously times by the revolutions you get power. So we're going to be working out work done per cycle in the start, just to get a feel. Let's say dividing the area of the turning moment diagram with the length of the base gives you the turning moment, right? Which enables us to find the fluctuation of energy, which we'll talk about. And the maximum order of the turning moment diagram gives us the maximum torque to which a crane is subjected to. This enables us to find the diameter. So when you're doing a design, for instance, and you need to find the diameter of the crankshaft, you're going to have to do a turning moment diagram. And once you find T max using this diagram, obviously you have to design your crankshaft. Otherwise, you have too much torque, and the crank will surely fail. So yeah, so that is just some application. So again, what we will be looking at here is the multi-cylinder thing, which is very important. Okay, so definitely coming in test 2. So a separate mounting diagram, blah blah blah. What this is saying is that the resulting turning moment diagram is the sum of the turning moments for the 3 cylinders. It must be noted the first cylinder is the high pressure cylinder, second is the intermediate, and third is the low. Doesn't really matter. In this case, they normally place 120 degrees out of phase. But here, there's 3 different cylinders. As roughly discussed, we've got the resulting turning moment, and that's from all 3 cylinders, which is basically showing you there. There's 3 different lines: cylinder 1, cylinder 2, cylinder 3. And what we basically essentially do is we sum up the torques, which you won't be doing. Do not worry. But then what's important is that it gives you this curve, right? Same with still a mean torque and still resulting moment torque. So just explaining exactly what's happening there. Yeah. And now they're staying again, the fluctuation of energy may be determined by a turning moment diagram for one complete cycle of operation. So we'll be talking about the fluctuation of energy now and what it is. So typically for this kind of stuff, we just take one cycle and we just analyze one cycle. We don't need to analyze the whole working of the thing. And then you will find the so-called coefficient or the fluctuation of energy, which is some kind of coefficient. Okay. So I think I explained this here already. Like I said, I literally said it in one slide, and I'm just going to unpack. Again, we have the same diagram as before. They've got the mean existing torque, which represents AF, right? And then there are important things to note. They're saying when the crank moves from A to P, that's on the first curve. If you have so from A to P, sorry, the first curve, A to P, or 0 to P, look at that. They're saying the work done by the engine is equal to that area under that curve there, right? Whereas energy whereas the energy is represented by, so the work done is A, B, P, whereas A, small a, big P, the basic block, the block there, right? That is represented as the energy required. Obviously, you can use the same principle for small p, big C, small q. But torque time, obviously, the area under there represents the what is this now? The work, and then the energy is the whole block there. And then what they're saying there, in other words, the engine has done less work, right, which is equal to A, big B, than the requirement. Obviously, it's below T mean. And they say this amount of energy is taken from the flywheel, and hence the speed of the flywheel is decreased, right? So that's quite interesting. But when it moves from P to Q, right, that is where, and I mentioned that, they're saying there again, the work done is small p, the work done is small p, big B, till small b, and then it goes down to C, and then Q, kind of the whole curve, under the curve, and if you want the whole thing, it's just going to be small p, B, big C. Yeah, don't worry too much about that. But then basically there, in that case, we've done more work. Obviously, it's an excess in energy we're referring to. And they're saying this excess of work is equal to that area over there, right? Obviously, we'll talk about the areas, but you don't talk about a big B, small b. It just sounds very confusing. And this is where the energy is stored in the flywheel, and hence the flywheel increases, and the crank moves from P to Q. So again, obviously, there's a deficit in the start, with the flywheels decelerating, giving the energy off. And when it comes at big B again, or big B, small b, C, the flywheel must now go fast again to absorb all the energy, right? So then from Q to R, more engine is taking, more work is taken from the engine. And obviously at that point, talking to the next point, they say the loss of work is represented by big C, small d, big D, capital D. And to supply that loss, there the flywheel must now decelerate. Well, the speed decreases. It gives off the kinetic energy to make sure we get that that steady mean, right? And then again, from R to S, right? What happens there is we actually absorb the energy. Flywheel goes fast again, and then the cycle essentially repeats itself over and over. Right, so again from S to E, the speed decreases. Is that clear to everyone? If you get that, you're 25% of your way there. Can I get a few thumbs up if you follow me? Thank you, Mr. Nevadis. So above the line, that's the flywheel absorbing. Below the line, that's the flywheel releasing energy. Is it all clear, everyone? Can I get some more thumbs up, please? If you lost, is there any questions? Obviously, like I said, I did say it to you before. I'm just kind of unpacking it over and over and over. So that is how we're able to keep a B talk, by the way, Mr. Kiefer. You'll be able to keep it, Mr. Haddon. That's how we're able to keep the engine at a specific torque. So, what they say, the variations of energy above and below the line, the mean resisting torque line, are called the fluctuations of energy. That is something you're going to be finding constantly. Delta E, which you'll be using in your calculations. Right? You have to find that. Again, it's above and below the line. So it's the maximum one and the lower. So I'm going to quickly, what they say there, areas which represent fluctuations of energy. Obviously, it's big B, small b, C. That's that curve. Anything above the line, the curve I was talking, anything below, which is big C, small d, D. And then obviously above that is the big D, small d, E. Those are the fluctuations of energy, right? And they can be a maximum and a minimum. So what's important to note is a little consideration will show that the engine has a maximum speed at Q, right? Or at S. What it means is that if you look at the diagram, so actually let's start at P. P is where it's at a minimum speed, right? And the reason why it's at a minimum speed at P is because it's given all its energy. But as soon as it comes at P, it needs to accelerate to absorb the excess, so it spins faster. And then obviously that goes from a minimum to Q, and therefore Q is a maximum. Obviously the cycle repeats again at R, and R is a minimum because it has depleted all its energy, and then it goes fast again. Spins, picks up momentum, so forth, and then at S is where it reaches its maximum speed, and then obviously it decelerates again. So just by looking at the diagram, you can gauge where those speeds are. The reason why we mention these speeds, right? Okay, so I hope you guys all got that. And what we're going to start doing now is doing the analysis of the diagrams, and here's a multi-cylinder. Very important, guys. Make sure you can do this. I didn't mention to you to sum of all the net torques, blah, 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 blah. We've got the mean torque, which is the low torque. We have A1, A2, A3, A4, A5, A6. And they say these areas represent some quantity of energy, which is either going to be added or subtracted from the energy of the moving parts of the engine. Right, the reason why is that energy, remember, it's torque times omega, which gives you Newton meter, which is essentially joule. Right, so remember, angle times torque, area under the curve, that'll give you some energy. That's why I mentioned that earlier on. So then let the energy at A equal E, not E, the point E. I don't like when they use it, point E, but what you basically do for this analysis is we start at point A. It's actually crap to talk about it like this, because the way I'm lecturing now, yeah, it's a bit strange. But anyway, it's just to find the maximum fluctuation of energy. So we basically we start at point A, we say it equals E, which is the total energy, and not E, the individual point. I'm going to say that again, E, not E at the individual points. I'm not sure why they actually did that. I've just called it X. And then we add the energies, right? So I'm just going to copy this diagram, and I'll just talk to you. Yeah, I'll just talk to it here so you can see it. This is the main. This is where Adam's minus. This is the procedure you need to use to solve these problems for the multi-cylinder. Very important procedure. And the idea is that we take E plus A1, right? We say plus small a1 because it's above the line. Then we say energy at C is E plus A1 minus A2, right? That's at the B part. And then at D, we say A1 minus A2, but that's below the line, plus A3, plus A3, but that's above the line, and then minus A4, which is below the line. At F, we follow the same thing. We say plus A1, it's exactly the same as before, minus A1, plus A3, minus A4 below the line, and plus A5. And obviously energy at G, we're going to find it's going to be plus A1, minus A2, plus A3, minus A4. It's all above, below the curve. So it's plus, it's above the curve, or then below the mean torque line, obviously. And in the end, you're going to find that your energy must come to 0. Right? And what they're saying there, you can't see now, but this is they suppose that the greatest of these energies, the fluctuations, will either occur at B and at least at E. And what you essentially do is if you look at B is E plus A1, and if you look at E is E plus A1 minus A2 plus A3 minus A4. If you subtract the 2, and then you get your maximum fluctuation of energy. So what it basically means is that your maximum energy minus your minimum energy within the cycle, and if you subtract the 2, you will get your change in E, which is your maximum fluctuation of energy. Was that clear to everyone? What it is basically. So you're basically finding the area under each curve, and then you're basically seeing under which area or which point does the maximum energy occur, and where does the lowest occur, and essentially just subtract them. That is titled the maximum. That's the maximum fluctuation of energy. Is that clear to everyone? Not so clear? It's not so clear, it's fine. Yeah. Okay, thank you, Mr. Manus. And from that arises a metric. And the metric is called the coefficient of fluctuation of energy. I'm lecturing university style now. You just talk, and don't do no example. And CE is basically that fluctuation of energy divided by the work done per cycle, which could be found using torque mean, obviously, times theta, right? And theta could either be 2 pi or 4 pi depending on the stroke. But the one we normally use is the work done per cycle, which is power times 60 divided by the amount of strokes per minute. But what's important is a new coefficient, and the coefficient is telling us how the energy is essentially fluctuating, and that is called the coefficient of fluctuation of energy. That's one of the main metrics we find. This is talking to the same thing. I've just literally copied this the last night, but it's basically the same thing in different words, really. E max minus E min, which is the change in it divided by your mean torque. Yeah. That's basically the coefficient of, yeah. What's important to note, for different cylinders, there are acceptable design, what's the word I'm looking for? Standards, design acceptable values. So when they design the engine and they do the analysis and they get the torque, they particularly want to find that the engine must fluctuate between certain numbers. So just being straight up 4-cylinder single acting 4-stroke gas engine, the coefficient shouldn't be 0.066. So on a more advanced level, if they're building the new vehicles, obviously when it's not electric vehicles, what they really look at, they'll do the torque diagram and actually measure everything up. They'll do the calculations and they say, oh no, our coefficient of fluctuation of energy is 0.2. Nope, that's not enough. We need it to be within a specific range. So that's the idea there. So that's just making away for different types of engines, the different coefficient of energies, which again, it's just what it essentially is, just the maximum fluctuation of energy divided by the work done per cycle. Right? That's what it is. So obviously, I've said this. The question was, how do we smooth out these fluctuations? Can someone just tell me? Besides the regular people, I've mentioned this obviously the whole time. How do we, Silas? How do we smooth out the fluctuations? I've been saying it. Mr. Doyle, I'm making you guys sleepy here. We smooth the fluctuations by something called the flywheel, right? That's what it is. That fluctuation which I was talking about, that's what it is. And I was just going to talk to this, and then what it says is that as the pistons reciprocate, they exert different forces and torques at each stage of the engine cycle. The largest amount of torque occurs at the powered stroke, when the piston is being forced powerfully downwards, rotating the crankshaft rapidly. So obviously I'm repeating the same stuff, so I want it to be in your brain. So without a flywheel attached at the end of the crankshaft, the rotation would be uneven, Mr. Kiefer. With a quick rotation at the power stroke, followed by 540 degrees of a relatively lackluster rotational speed of each piston. So the flywheel uses high rotational inertia, the I, to even out the torque delivery, so the crankshaft rotates in a more constant, smooth fashion. Furthermore, also to keep your engine running smoothly when you're not supplying fuel in neutral. That's what your flywheel does. Your flywheel is constantly spinning two ways to ensure that you get a nice, constant, torque. So that fluctuation, I did mention to you what it was, and now we're touching on the flywheel. So I'm going to talk right through them and obviously just start solving examples. So a flywheel is used as a reservoir or energy storage unit, which stores energy during the period when the supply is more than the requirement and releases it during the period when the requirement of energy is more than supply. Obviously, I did say this right up front, but I'm obviously unpacking again just to say that's what the actual flywheel is, right? Again, it's nothing to talk about there. But again, over here, more the last part is, for an example, in an IC engine, the energy is developed only during the power stroke, which is more than the engine load, and no energy is being developed during suction, compression, exhaust, or there's only small negligible positive energies. The excess energy developed in the power stroke is absorbed in the flywheel and then releases it to the crankshaft during other strokes when no energy is developed. So that's what the flywheel is essentially doing, and thus rotating a crankshaft at uniform speed. That's the main aim of all what we're doing here. Someone's going to ask, what did you learn today? You let him talk about it. You say, no, I've done the analysis on excess energy developed during a reciprocating engine, really. And also thus rotating, and saying another consideration again, we know when it increases and we know when it decreases. And then again, lastly, put the point and say, hence a flywheel maintains a constant speed, which simply reduces the fluctuation of energy, right? Did you know that? It maintains a constant speed. So, what flywheels are used for? I'm not going to talk to this, it's from Wiki, but basically what I want to highlight again, provides continuous power output in systems where energy source is not continuous, right? Which is our input in our crank. It's also used to supply intermittent pulses of energy at power levels that exceed the abilities of its energy source. That's another type, another example. So I don't want to talk too much on that. So here again, I said, hence the flow does not maintain a constant speed. It reduces the fluctuation of speed. Sorry. That's what I was thinking of. In other words, a flywheel controls the speed variations caused by the engine turning moment during each cycle of operation. I was concentrating myself, I knew something was wrong. So it doesn't maintain a constant speed. It reduces the fluctuations. That's what it does. You might ask why it's important. We've got another friend on the other side, it's called a governor. And the function of a governor is different from a flywheel. A lot of people think of the same thing, because a governor regulates speed, the mean speed, when there are variations in load. Whereas a flywheel doesn't maintain speed, it talks to fluctuations rather, right? So just examples between the flywheel and a governor. It's not really important. You don't have to know this, but this is for more information's sake. Just going to highlight the salient points. A governor, let's say, control the supply of fuel to the engine. That's one. Obviously, flywheel has nothing to do with fuel. They're saying the flywheel, the operation of flywheels is continuous from cycle to cycle. On governors, that's intermittent. So we don't always need that. Speed controls in one cycle. Of a governor, speed controls over time. And the governor operation depends on the variation of load, where the flywheel does not change in load or output. There's nothing to do with that. And then the last, basically, they say there that the flywheel reduces the fluctuation of speed during thermodynamic cycles, but it does not maintain a constant speed. So flywheel doesn't keep a speed constant. It's not its job. It's making sure that the fluctuations at T mean, and make sure that we get our T mean. We could even say it maintains a constant torque, arguably, right? More examples, same thing. It's just the same, all the same stuff. You can have a look there. Flywheel contains change in speed over time. Governor just control the change in speed. Governor is an essential part of every prime mover, where it's not on the other side. The flywheel stores the engine, gives up when required, whereas a governor doesn't do things like that. It just regulates the speed by regulating the quantity of working medium of the fluid. So basically regulating the fuel supply. So add more fuel, more load, so forth, so forth. Okay, another metric which is giving birth by it is called the maximum minimum speed. And this is this talks to the maximum speed and the minimum speed in the cycle. Obviously the mean speed is going to be the max plus min divided by 2. That's obviously the minimum speed. That's the omega you normally use in your calculations, that mean speed of the engine. But the max speed, but the coefficient of fluctuation of speed, which is not spelled right there, the CS, which is N1 minus N2 divided by N. So let's say the coefficient of fluctuation of speed is a limiting factor in the design of a flywheel, and it varies upon the nature of the service into which a flywheel is employed. The reciprocal of the two is just what? It's just a coefficient of steadiness. That doesn't really, we don't really talk about that a lot, but just be aware that there's something now called the coefficient of fluctuation of speed. What's important here is that we've got a model there, and that model is change in E, mr squared, omega squared, CS. Now I want to just paste something else there, and it's the model we will be using a lot. It looks like this. I'll show you. Yeah. So you have to calculate this. Obviously, that's why I'm mentioning it to you. But what this page essentially is over here, guys, just deriving deriving this formula. Okay, we at the end now. But yeah, what they basically do, they take the kinetic energy of the flywheel, they take the maximum kinetic energy minus the minimum kinetic energy, and all we really get is I omega squared, which is the mean speed, and then something called CS, right? Obviously, they take the I, you can make the I into mass times radius of gyration squared, and then yeah. So that is how we actually find the maximum coefficient. That delta EX is the fluctuation in energy from minimum to maximum. So you might ask, what is Mr. Scout talking about? So when we do our diagrams, you know that multi-cylinder thing, we find the maximum fluctuation. We find the fluctuation of energy. From that, we're able to design our respective flywheel. As you can see, I is mass times radius. So sometimes I ask you to find the mass. Sometimes I ask you to find the width. Sometimes I ask you to find the thickness of the flywheel. So the whole point of all of this is to basically find out what is the size of the flywheel I must use. So if I have a certain engine, I do the analysis, the turn, the crank, if a diagram, and then what flywheel should I actually use? Boom. This model will tell you the mass of the flywheel, basically. The size of the flywheel and so forth and so on. Okay, again, talking to the coefficient of fluctuation of speed, it should have been up. Different machines have different fluctuation of speed. I should have mentioned the slide before, sorry. But yeah, electrical machines has a very small fluctuation of speed. Arguably that could have been a slip. Electrical machines 0.003. Machine tools have about 0.03. Punching, shearing, and power presses also is their flywheels. If you think about that also has you know, some fluctuation of speed. It's all acceptable ranges. So I just want to take that for my sanity, and apologize, should have been over there. In terms of flywheels, there are predominantly two types of flywheels, the disc type and the arm type. I'm not sure if you guys have seen both. What they say that the weight of the flywheel is mainly located in the rim and the arms and the boss, which is the center. Typically don't really you know, it's not really of the core focus. Doesn't absorb a lot of energy. Why is that important? Because when we do analysis, they're going to be talking about the breadth and the thickness. So I'm showing you there the rim type. There's a B and a T. That's the B and the T. So we look at the, you know, the pi D circumference times BT or BT, whatever. Yeah, I guess that's the whole volume, but yeah. We look at the rim. The rim is what is the core focus of a flywheel, not the actual center part. Again, fluctuation of energy. I mentioned this to you. Obviously, you can see that I'm just lecturing through everything, and then obviously we'll touch on examples and just refer back to slides when need be. But the fluctuation of energy is essentially equal to the mass radius squared, which is I omega squared times CS. The mass itself can be expanded upon further, which is 2 pi r, which I mentioned to you, which is the circumference times the area. We'll talk about which area times the density. Typically looking at cast iron or steel. So your densities for those are 7260 or 7,800. Make sure you remember that. 7260 for cast iron, 7,800 for cast steel. The area, again, like I said to you, it's the breadth times the thickness of the rim. And what I mean by that is this image over here. And yeah, so they sometimes say that they normally take B over T is usually taken as 2. But it's normally told you. They say when the flower is used as a pulley, it can happen. The width of a rim should be taken 20 to 40 millimeters greater than the width of the belt. So that's a B and T they're talking about. The reason why this is here is because you're going to have to get these dimensions. First principles analysis of what's happening here, basically of the dimensions of the flywheel. It's exactly the same thing as before, but what's important of this, what they really talk about here is that within the flywheel when it spins, the reason why you probably did your hoop stress is that you can see there the vertical upward force presents a tensile stress or hoop stress, or also called centrifugal stress or circumferential stress, which is your omega r, your what is it again? Rho, is it the rho v squared? If you remember that, and then they basically expand upon that, and then you just basically get all of that. So that's where it all comes from, these formulas. So just in case you're thinking, oh no, it's all just magic, but they basically look at the centrifugal stress which is the rotational hoop stress, and then kind of plug and chug a few values, do some integration across the thing, and boom, we get that pi dA. And obviously A is B times T, which is the cross section of the rim, the width of the rim, the thickness of the rim. Why is the rim? Because the arms and the boss doesn't store a lot of energy. Most of the weight is stored along the rim. Okay, that's just the table, and yeah, finally done. Is there any questions? Oh, hour of talking. Any questions, guys? None? There was no one listening. It's probably sad, eh? Bradley, Mr. Kiefer, Mr. Bali, Mr. Manus. Great stuff, great stuff. Okay, guys, there's no questions. Fun questions. I'm just gonna give a 10-minute break, just to comfort break, quickly stand up, because from here on out we are just moving on examples. So we're looking at several examples. 1, 2, 3. There's 2 there. Another one there. Another one there. We'll be looking at all different types of examples. Some advanced examples. Some 7 or 8. 4-stroke. So that's basically that, and that's the end of the chapter. So we've basically I just talked through the whole thing, because I know that it's all out of the way. And if you're lost, obviously I will try to refer back to where we need to be. But in this time, just get your formula sheet out, maybe, just so you can work with it, and obviously your textbook as well. Okay, I'll see you at 22, and we can start, and obviously get your pen and paper ready so we can actually start solving. So this can, for part 2 of the session, and part 3, we are just solving problems. Okay, guys, thank you. See you.